That's slides on molecular dynamics, not from this one.
Okay.
Oops. Thank you.
Okay, well, thanks for coming. Today is a special meeting because we are going over basic skills that we use in our everyday life. Hopefully, if we are dealing with computational chemistry. And most of you were coming through such activity in the past, but since we need to make sure that there is a continuity between coming and going papers, we are just making a refresher, going over some basic skills and trying each other to go through them. So the program is very ambitious. If we will not fit into the allowed time, then we may continue next week. And main program for the next week will be sharing, editing and discussing posters for local conference. So who is presenting? 3, right? Okay. So we will have 3 posters and are leftovers from today. So the program for today, well, we will skip the preparing atomistic models because it is what all of you are doing every day with Avogadro or some other like Gauss-U drawing models, and then so the plan of all meetings is as follows. We are not going to look onto any, we will look only on specific computational chemistry software, VASP, which is Vienna Initial Simulation Package, implementation of DFT, and we will quickly refresh basic skills how to convert models from XYZ files that most of us can create into input files for the software. Then we'll go over basic ways of analyzing software, specifically looking onto density of states. And then if we are interested in optical properties of materials or their suitability for applications like sensors or photovoltaics, we need to see simultaneous description of ability of material to absorb light and to dissipate energy into nuclear vibrations. So it will be simultaneous description of radiative and non-radiative transitions, which will be which we are doing through non-adiabatic couplings. this is also connected. This cannot be done without molecular dynamics. And since some of the models that we deal with are either heavy atoms or open shells, like high spin configurations, we need to take special treatment of spin, or if spin is not a good quantum number, so-called spin-orbit coupling. 2 hours is very small time interval for this ambitious program, but we will make a refreshment, launch discussion, and maybe keep interacting further to, at least we will be able to identify our strengths or weakness in some aspects, and then we will decide what to do next. So the all slides are uploaded to the station. John? Oh, John?
Yes.
Okay, your image is frozen. Now it is not. Do you see the shared content?
Yes, I do.
Okay, very good. So the slides are numbered. So if it is, and then you click on this little button to start slideshow. The first presenter is Fatima, and she will introduce us to the world of VASP. If you don't mind.
So I'm going to explain today how to convert XYZ files into input file for VASP, periodic boundary conditions, input files and output files. In order to make XYZ file, we can use different software like Avogadro, Vesta, and we can save the model as XYZ file. Then we can copy this file to the directory in VASP, and we can sort it as we can see here. These atoms are like their silicons are and hydrogens are scattered. So after sorting, we can see these atoms are organized. First all hydrogen atoms, and then all silicon atoms. And we can save this file as oscar.xyz. After that, we can use this command to make a Oscar file. Here we can see these are the first line. You can see the name of the atoms, and second line, this is the lattice constant or scaling factor, and then we can see the lattice vectors. We need to multiply the lattice vectors by the scaling factor. After that, we can see the number of atoms. Here in this case, I have 8 hydrogens and 3 silicons. Then selective dynamics, it means we can choose whether or not molecules are moving in all directions, or they should be fixed. So true means we can see, as we can see here, all of these are true, means all of these atoms can move in all directions. This is a Oscar file, one of the input files in it. Now, periodic boundary conditions. So periodic boundary conditions is used to simulate processes in a small part of a large system. All atoms in the supercell are repeated throughout the space to form an infinite lattice. Here we can see the wave function, it's a plane wave function, and this T is a translation vector. So is it okay to continue?
Yes, please keep going. You're just hiding.
Now-
You're hiding from the camera, and it is hard to follow what you're talking if what speaker is talking without visual.
Now here we can see a sample of Incar file. First line is a system, and the second is different values to determine the optimal lattice constant. And at 200 we can see this is energy cutoff for the valence electrons, and then this 2 is for algorithm for geometric convergence.
Can I interrupt you?
Yeah, sure.
So, which boundary conditions are? Do you use any specific boundary conditions in this example? If you scroll 2 slides back. Yes.
No, like here we have a big one. Like
So
in
this
all
one is
directions.
equivalent to like just a molecule.
Molecule, yeah.
What will be how this numbers 888 would change if you would have like a bulk or one-dimensional nanostructure?
So if we can choose any axis, X, Y, or G. If we choose
No,
X.
the 3 numbers at the end, 888.
So for nanowire, it should be one-dimensional. So we can choose any of them at 0.
Huh?
Not
What?
0.
Just repeat. 0?
No, not 0. So we need to make a model and optimize it, then measure the length.
Okay, so distance between periodic images,
Yeah.
which is approximately equal to bond length. Okay, please keep going.
And here we, as I was explaining, like these different parameters. This NSW is the maximum number of geometric iterations to take. Ice smear is Gaussian smearing, and sigma is the degree of smearing, and L real means whether we will choose real space or reciprocal space. If it is true,
Can I interrupt? A little comment. So we are here only to share our own experience. If you found something but you didn't practice it, do not report it. So report only those keywords that you know that you tried yourself.
okay.
We all are literate. You can go to Google and find things. Only share what you did yourself.
Okay.
Point what is important.
Okay. So
Otherwise, we will fall asleep.
So here I chose true. True means it is real space. And then I chose 0. So wave functions, I defines wave functions from the wavecard file in read. And here L waves true means wavecard file will be saved. And L charge how to initialize the charge density for a calculation. So it will take the charge density from the charge card file. And this is the E difference is convergence criteria for the geometrical characterization.
Good. It is all correct, but you know you were working as TA during your graduate studies. You know, if you shouldn't be boring.
Okay.
So first you should tell like it's all correct, but you can just take a template, copy paste, and forget what is written there. Templates of these files are available, and you can run job successfully without knowing all these details. But if you're curious, I can tell you details. Right? You're teaching us.
Okay.
Okay, go forward.
And here we can see the key points. I selected automatic mesh 0 means the key points will be selected automatically. And then
And you're sure that we all know what is key point?
yeah, it's in the key space.
No, you can ask later. Raise the hands who know what is key point? Raise the hands who do not know what is key point.
I
Ask
assume
us.
all of
Ask us. Make sure that there is a contact with the audience. You're not telling it to me. You're telling it to Daniel. Ask him if he knows what is key point.
I don't know what K point is.
Quickly tell what is key point, please.
So key points, it's we have for lattice we have real space and reciprocal space. So in reciprocal space, real space is Cartesian coordinates, and in reciprocal space it's momentum space, and so we can select different key points there. K means wave vector in momentum space.
Makes sense or not quite?
Makes sense.
So if we have isolated molecule, electrons are sitting on it, right?
Yeah.
But if you have a bulk, small piece that is repeated, electronic system as a whole can move with constant velocity and nothing will change. So if we are talking about molecules, we don't care about key points. But if it is about where electrons can, in ground state, can move continuously, then we need them. Good?
Yes.
Okay, keep going.
Then it's Potker file. So here in bus, so all of the CD potentials are given, so we can select. Then, but we need to make sure one thing, that the order of the pseudo potentials in the Pascal file and Inker file should be the same. Now,
Where are you taking the potentials for this podcast file?
from where?
Yes, where do you get them?
It's given in the
By whom?
bus. In bus.
No, where? In which directory or which website? Okay, it's question for future. Where to take the potential?
Fine.
Huh?
Fine.
Where?
Okay. I'm not sure.
Okay, we'll discuss it later. Where to take the potential? Please keep going.
Okay. And this webcar file, it is output file. So all wave functions used in bus calculation are stored in this file. It is useful for continuing calculations. Otherwise, the initial wave functions will be taken from the charge file or initialized randomly. So it is necessary for band projected charge density calculations. So sometimes this file is very large, up to several gigabytes. In that case, we can select whether or not the information will be saved by selecting NF false in Inker file. Now outcar files, it is also output file. So all details of past calculations are saved in outcar files. So it contains a lot of things. First of all, details from all the input files, and then nearest neighbor table, and then electronic relaxation iterations. Finally, it calculates the Coulomb forces on each ionic core.
Okay.
Now charge curve file, so it contains the charge density information, the lattice vectors, the atomic coordinates. So it can be used as an input for further bus runs, or if it is convergent successfully, then we can analyze the charge density using this file. And we can visualize the isosurfaces. We can calculate charge densities for a particular band. If we select in Inker file L per equals if it is true, L product is true, then. So, but we need to, if we take this one, if we take this charge card file, then we need to provide two other files. Those are webcard files and charge card files. For dynamic simulation, the charge density on the file is the predicted charge density.
You are reading the slides? No, please do not do it. We all are literate. It should be different. One thing should be shown on slides, another one, it should be a live speaking. You never look on your own slides. You come here, approach the audience and explain. No. Reading the slides is the worst possible things. You need to tell only things from your heart that you know, that you memorize. Reading slides, then we can, now there are computer programs that can read texts. It doesn't count as a presentation. Next slide, please. You already read what is here.
So,
Look on us, not on slides.
so it is partial charge file, density file. So using this file, we can make STM images, scanning, tunneling, microscopy, and scanning, tunneling, spectroscopy. So, in order to get this file, we need to copy count card file, coordinates of count card file to postcard file, and we need webcard file from previous calculations, and we need a couple of parameters in our input file. Those are here, like that.
Okay. Is it last slide?
Yeah.
Okay. Let's thank Fatima for very vivid, interesting, and useful presentation. Are there more questions? If not, thank you. Please go forward. But we need to have 5 more speakers in another 90 minutes.
Yeah, I was just, what does it mean by par charge is the same as a local density of states? Like, I don't know, I just don't see a connection between the two.
She can answer it for sure. It's her topic of her thesis.
What is the question?
Explain what is local density of states. This, let me make introduction before she answers. In the community of experimental workers in the area of scanning, tunneling, microscopy, there is a colloquial language. There is a concept that only they are using in their professional work. Local density of states. It is a little bit different from regular density of states that we are using in our life and our colloquial language. So your question is, what is local density of states?
So we know density of states, right? So the number of states per interval to occupy by electrons, that's the density of states. But local density of states is localized, like space dependent.
So it's like specific to each region of a sample?
Make sense?
Yeah.
For example,
We did
if
in our class. We did that same thing in our computational class one time. That one.
Not much. We could, but we didn't. For example, if you have a system of donor and acceptor, and you know that total density of states is summation of those of donor and those of acceptor. But if you put your measuring tip near, let's say, only acceptor, and run this STM experiment, you'll measure only density of states of those orbitals that protrude in the vicinity of your tip. So it will be not everything, but only those orbitals that are distributed in this vicinity. And indeed, vast calculations allow to do these maps, to reproduce results of STM experiments. Maybe it's the main reason why Fatima is interested in calculations.
Yeah, it's something related to my research. STM, STS, local density of states.
Okay.
More questions? If not, thank Fatima once again. So next presenter is Dave. and he will stay on the same general direction, but he will give more practical advices to all of us, and he will also introduce the concept of regular density of states rather than local density of states.
Alright, so just a little rundown of what we're going to talk about here. Different types of jobs. There's the ones you see here and many more, obviously. The main difference between running these jobs lies in the in-car file. At least that's my understanding. We can get in-car files from inside of VASP, so we have them in the bin. I'll show you how to get some of those here shortly. Are those showing up green? That looks the same color. Okay, well, so what we talked about earlier, you build an Avogadro, build a cell using Avogadro or similar software, upload it into the desired directory, and then obtaining the POSCAR file. As such, you actually went through that. Fatima did, so don't need to go through that. Okay, so optimization. Here are some of the codes that you need to submit in order to get a video of your optimization. If you want to watch your geometry optimization, then you can go through these steps. We talked about the podcar files where you get your potentials. You can take them right out of the directories underneath Dr. Keelan's name, I believe they're in there. So you can use that CAT. You see in the second line. And here I just give an example because there's a C here, that's carbon. So if you have a carbon atom, you need to do C, and then if you have hydrogen, oxygen, nitrogen, you need to do that separately, that same line for each one, changing that letter to the atoms number, or atoms letters.
Can I make a brief
Yes,
comment?
please.
So these directories with potentials are, we can set up any directory. We can put it on a personal computer, and same as like you may to buy a garage to put your car, but it is not defined where you place your garage. So when you purchase the license, they give these files, but then you distribute them on your directories as you like. And they have subdirectories for each element, and each element has a spot card. And now Dan is showing how it is set up on the South Dakota cluster. When we go into different system, it will be arranged differently.
Oh yeah, I should mention this. All the codes that I'll be presenting are for the South Dakota cluster HPC. They differ slightly using other clusters. So after you...
Looks like John had a question.
Oh, John, what's up?
Does the ordering of how you bring in the POTCAR files matter?
I'm sorry, why what?
How does the order in which you load in the POTCAR files matter?
That's a good question. I don't think so. I don't think it matters. I guess I always do it in the order that when I sort my file, when I sort my POSCAR file, I try and do it in that order, but I don't think it matters, does it?
It's very correct.
Okay.
So the VASP is a silly robot. It is not thinking for us. So if you make mistakes, it's our responsibility. So when you are looking on your POSCAR file, it lists atoms of element type 1, element type 2, and if you the name of the element that you type, like carbon, hydrogen, it's nothing. It reads type of element based on contents of POSCAR file. And if you swap orders of hydrogen and carbon in benzene, then you will, it will mean that you will start to compute the molecule which has 4 hydrogens inside the ring and carbons outside. And you cannot blame VASP because they just tell here is the list of elements. If you swap the, and when you do it for some advanced calculations and discover 3 months after starting calculations, you see some surprises, like model is exploding or does something that you are not expecting it. Please keep going.
Question. Thank you. All right, we'll just watch a short little clip here, only a couple seconds long, of optimization of 4-hydrazine for dinitrogen tetroxide molecules. Doesn't move very much. It's good, but you see them separate out a little bit, get some distance between them. All right, so spin orbit on the left side here, we see just copied in-car file for the spin orbit. My understanding is that the important one here to look at is this LS orbit. If it's .true dot, then it specifies that there's spin orbit coupling taken into account, and if you change that to false, then it doesn't take spin orbit coupling into account. So, orbitals. So on the right side here again, there's a screenshot of what the in-car file looks like. You see the NSW here, the number of steps. Right now it's 0. You want to change that.
No, you don't. If you need orbitals, you need to keep it NSW equals 0.
Okay. But the number, the hashtag EINT, that number is your HOMO-LUMO gap. So if your HOMO is at minus 3.2 and your LUMO is at minus 1.5, you got to change those numbers to accommodate that.
Do you need to match it literally, or you need to give some breathing space and make it a little before and a little after?
Yeah, a little before, a little after.
Okay.
So when you're looking at the outcar file, when you open up the outcar file, you'll see your gap will start to go down. So it'll be like, it'll all be 2s on the right hand side generally, or in my experience it is, and then it'll go from like 2 to 1.9, 1.7, 1.6, and then once it gets to 0, so it's nice to get like 2 or 3 that are still 2s and 2 or 3 that are still 0s, and get that gap.
But the example of in-car is not from your personal calculations.
Correct. That's straight from the bin.
Yes, because your models never had number of bands equal 1,200.
No, I just took that right out of the bin.
So which number of
of
bands is typically in your systems?
Number of bands, I think it's like 300.
Okay.
I believe. So, okay, yes.
Why your energy is like positive energy in this interval?
So the second to bottom line?
Yeah.
Is that this one here, or this bottom line?
Is there, you didn't use this one, or you get it from?
Yeah, this isn't mine. This is just straight. If you were to take an in-car,
Why this energy is positive in this case?
The energies listed in the outcar file are not yet shifted in the right way. If you add alpha plus beta, which is typically a negative number, then they will be negative. The question of Javed originates from the idea that if something is stable, energy should be negative. So typically, if you see positive energies, it means it is something ready to explode.
oh, okay. All right. So with orbitals, you have to run geometry optimization first, and then you want to copy your potential. Your pod car, postcard, K-point, wave car. It's listed here, as we see, and then there's just a couple codes how to visualize your orbitals. I'll show you a little bit more on the next page, but these are just this par charge 0.0096. That is just one specific point, so that this part here will change depending on where your HOMO-LUMO gap is at. For this example, par charge 96 was the beginning of, so it was like HOMO exactly.
The number of band, right?
Yes, 96 is the number band. Yep.
What's the function of this command?
I'm sorry?
I guess what's the function of this command? Is it charge to cube?
Charge to cube. So it changes it into a .cube file that you can use in like VMD, the visualization software, so that you can actually see it.
Gas views format.
Can I? Yeah, Javid is right. Most of us directly plot per charge files in the VMD, or in past we did vast view, but some people are coming from the background of Gaussian and Gauss view software, and the orbitals, molecular orbitals files from VASP are in very non-standard style. They need special software to be read, but this charge to cube convert from VASP style to Gaussian style. So the users of Gauss view can plot orbitals in the same way as they did before. Make sense?
Yeah, and when you type in that command, the VTools 3, when you type in that one, it'll prompt you to enter in the number of atoms. So, for example purposes, the hydrazine combustion only had 3 different atoms, just hydrogen, nitrogen, and oxygen. So you do 3 atoms, 3 types of atoms, I guess. Shouldn't be number of atoms, types of atoms. And then it'll ask the atomic numbers of those 3 that you entered. So it'd be like 1 for hydrogen, 7 for nitrogen, 8 for oxygen. And then you can just download that cube file to your computer and use a software like VMD to visualize it. You kind of want to just mess around with VMD if you've never used it before, but ultimately, to get to the point where you want to mess around, this is good to know. You go to the graphics, representations, and then drawing method, and choose isosurface, and then you can play around with it a little bit and see how it looks. All right. Oh, fun. Okay. So now we can talk about density of states. So some of these need to be addressed a little differently than what I have them written down right now. So these are just commands that you want to follow. The in-car file is the in-car spin, is the one that you're interested in for this. And you see, yes?
What is density of states? Can you give definition before you go into technical details?
Yes, so density of states is the occurrence of the energy levels at different intervals. Is that
Yep.
good?
Please stop the speaker, any of the speaker, if you like. So, 10 minutes ago, you were speaking about homolunar gap and a list of orbitals that have occupation like 2, 2, 2, and then 0, 0, 0.
Right.
So, from point of view of computational chemistry, a molecule is not a set of atoms. It is a set of levels, some of which are occupied, some of which are not. And one specifies them by energies. So if it is very small molecule, we can list or draw each orbital as a horizontal bar line. But if there are thousands of those, you will be tired to draw them, and even if someone draw them for them, you will be tired to watch. So density of states is nothing but a way to represent large number of levels. When they are dense, then density is high. When they are sparse, density is low. Okay?
Okay.
Keep going.
All right. So on the in-car file on this one, you see on the right-hand side again, main points here on this one is the I spin equal to 2. So I want to clarify, I'm not positive on this, but I spin of 1 would be no, and 2 is yes. Is that correct? Okay. and then your N up down, you want to change to 1, 2, 3. So this part, changing it to 1, 2, 3, I took directly from Stephanie's
That's
presentation.
correct. Can I
Yes.
just make a comment for Daniel? So if you are experienced in Gaussian, the things that Dana telling right now, the number 2 corresponds to letter U in the type of method, like U B3 or unrestricted. Okay?
Yeah.
And the N up down equals 1, 2, 3. It corresponds to at the beginning of the Gaussian input you have charge and multiplicity. So this 1, 2, 3 is multiplicity, second number of those two. Make sense?
Yes.
Okay, keep going.
Okay. So then you want to copy your outcar file as a states file. This is where the rest of this slide kind of gets iffy on what's going on. So you want to go into your states file then and delete unneeded stuff, making it different than your outcar file. What you want to keep is that homo lumo gap, but like 10 before, 10 after, about 20.
You can take 100 before and after, depending on
Does it just
how,
change
how
the
curious you are.
Does it just change the calculation time, or
No.
your whole graph would be longer then?
Yeah, it just
Oh,
shows the range.
Okay, I see. All right, so yeah, you just choose the points that you're interested in. Then, quick question, anybody that can answer. DD is the delete row. How do you delete mass amounts at once on there? Because if I like highlight it and just click delete, it doesn't work that way.
So if you wanted to delete 100 rows, you would do D100D.
Okay. So you just like,
If you want to delete 2 lines, you do D, number 2, D.
oh, you
And
hold
you
it down?
Huh?
Or you do
We're not
it
done.
No, no, no.
or what?
You-
I was like trying everything. I could not get it figured out.
These buttons were designed at a time when either people were not sober enough to click the mouse, or when the mouse was not designed yet at all. It was only the keyboard.
Or you can use the U to get undo anything.
You can use what?
U for undo.
Oh, I didn't know. That's good to know.
Simple.
Cool. All right. And then you can take from the bin your dress DOS norm file. If you're using just states, if you're doing states up, states down, then you want your DOS down, DOS up files there. And then when you submit those codes, it'll ask you for some information, which I have below the next one, which is not right. So your line width, use 0.1, magnitude 1. It'll ask how many atoms are in, not how many types, but how many atoms. So it might be 400. And then the number of electrons, which you can determine using the grep Neal outcar code. And then I don't know what gap bulk phase is, but it's equal to 3.
What is N up down? Equal to 3.
What is what?
There's one tag N up down 3.
And up, down.
Anyone wants to make a comment?
Where are you seeing that at?
In your in-car file.
In-car file.
Daniel knows.
Right above the iSpin.
Oh.
Ask Daniel.
Just mean the charge?
Not charge, multiplicity.
On
Oh,
the spin.
okay.
Unpaired electrons.
And yeah, how difference in number of electrons in alpha and beta.
No, fine.
Difference in number of electrons, alpha and beta.
So let me make a comment, because things are new and heavy for Dan. So he tries to be very general and make his presentation working for any case. And one of the relatively general cases is when you allow electronic configuration for alpha and beta spins be different. For 90% of jobs, we may avoid this specification, and we assume that alpha and beta are equal, and then you just do not have this down or up. You have just one list of orbitals, as you told before.
Yes.
when we do have spin projections, you have a list of orbitals twice. One for spin up, another for spin down, and they may differ in energies and in occupations. So you're presenting something really advanced. But in most cases, you can skip it and do as you did in your practice calculation half an hour before the meeting.
Yeah. Okay. So that and up down equaling 3 changes your results how? Versus if you had it equal to 1.
Okay.
Sorry, presenters asking questions now.
Okay, I'll take the question and answer it. Stay here because there could be questions, other questions too.
Okay.
Here? No.
It doesn't want to
Try in the middle of the screen.
no, it uses it not as pen but as
Okay, I'll take by fingers. So you have orbitals, and you can place the electrons, 2 electrons on each orbital, one with spin up, one with spin down. But if you want to have 1 electron with spin up more than spin down, right? 1 unpaired electron, it will be your n up down equals 1. So up is bigger than down by 1.
Oh.
And it will be doubled multiplicity. If you have two more spins up than spin down, it will be number 2, which will correspond to triplet. Right? And the rest of numbers are too exotic, like quadruplet. You do not want to mess with it
Okay.
unless you really need.
Okay, well then we're at the point now where you could type in this second to last line and it will give you a .ps file as an output, and then you can convert that .ps file to a PDF file, and it will, once you download the PDF file to your computer, then you can just visualize the density of states graph like that.
But this one is without up and down. It is for non-spin polarized,
Yes.
or for singlets.
Oh, yeah.
Okay. And for which system is it?
The hydrazine, hydrazine 4-dinitrogen tetroxide.
So it's your own system.
Yes.
Okay. And if Jabat will ask why the homoluma is at positive numbers, you can say it is hypergolic fuel that is going to explode or burn right away.
Alright. And then with spin orbit, seems like pretty much everything's the exact same except the in-car file is different in that you use the spin orbit one for the bin instead of just spin orbit coupling. So, yeah. Is that accurate?
Okay, let's thank Dane. So, any questions? Anyone who wants to?
You are the only
this?
participant.
Can I look on the density of state one more?
Can you what?
That image, density of state image. Is it blue line is for unoccupied orbital?
Say that again.
Is it blue line for unoccupied orbital?
There is no blue line here.
I mean green one? Yeah.
So
Green
yeah,
line?
the filled portion is occupied and unfilled is unoccupied.
Okay. No, I was wondering why green line is going below the red line.
Or it is not going below.
I mean, on the other side, it seems like they have a blue line, green line too.
Blue
So
man, freaking me out here.
Is it the border of the white and
Yeah,
red
it goes-
line is like,
The green one goes all the way over. Is that what you're asking?
yeah.
It's just a default from new plot. You can change it to have the lines be different colors if you really want to.
Okay.
So can you scroll, Dane? Can you scroll one slide back? So second line from the bottom: GNU plot, bin GNU prog, blah blah blah. This is a little script. This GNU prog. It is maybe 3 lines. You can make a copy to your directory and modify it as you want. You can set up colors, which are like red, green, blue. 1 is red, 2 is green, 3 is blue, and then there are other colors, and you can change many other things.
This is a typo as well. I just noticed this PS2 PDF should be WR, not OR.
Yep.
That's all I got.
John has a question today.
Well, so just one comment. So when you were talking about that line that says the gap bulk phase, so that's not always 3. The way I understand it is, depending on what material you're looking at, you put what the bulk band gap energy would be in that line.
Oh, okay. I'm gonna write that down. That's good to know.
Unless Dr. Killen has a different answer, but that's the way I believe I remembered it.
Yep, that's correct.
You said it was the Fermi energy. Is that what you said?
Gap for the same material of the in bulk phase.
Yeah, so like if you're working on a quantum dot or some other type of confined material, whatever in the 3-dimensional bulk, that would be the value you'd put in.
So these parameters, they will not change position of the gap. They are made to adjust the height in order if you need to compare systems of the same composition but different number of atoms. Like if you have 10 or 100 molecules of the same type in the same cell and you want to compare them. Evidently with 100 molecules all peaks will be 10 times bigger and hard to compare, but if you scale down, it will be much easier to compare.
Cool.
More questions today? If not, let's thank you once again. And now we have a super marathon. We have 4 presentations for 1 hour. No more than 15 minutes per talk.
I tried to keep this one short, guys. I'm sorry.
So, next one is Aaron. In fact, he presents 3 chapters today, each of which altogether should be no more than 15 minutes.
Hopefully not.
And the first chapter he presents is in some sort of continuation of what previous speakers did, is how to plot orbitals without converting it into Gaussian style, right?
Mm-hmm. Yep, and yeah, so yeah, we'll be talking about how to plot orbitals from that you get from VASP. And initially, well, the ones I'm going to cover is spin independent and spin polarized. I think I was scheduled to do spin orbit coupling orbitals as well, but I'm not really quite sure how to do that. So if anybody else has any idea how to accomplish that, let me know. So the input files in the software that you need to plot orbitals generated from VASP. So to get orbitals, you need to get the par charge files from VASP, which we've seen how to get those from the last couple of presentations. Then to visualize orbitals, there are 2 convenient software choices that I find: Vesta and VMD. Vesta is, I find it to be simpler to use, but VMD is more versatile. So for the presentation today, I'm going to be using VMD, because to do spin polarized orbitals, you have to use VMD. Vesta doesn't give you that option. So basically the rest of this presentation will just be going through like visually how to plot orbitals in VMD. So this is kind of a rough idea of what you'll see when you open VMD. You have
You will see this football stadium.
well, if you're on my computer, you'll see that. So there's a command line that always runs in the background. If you're crafty enough, you can play around with that to see if you can specialize visuals the way you want them. And then here's just like once you upload your par charge files and your pause card, this is where you visualize them. And over here is where you load things into. And to begin with, you want to click New Molecule because we want to load a molecule in. And then that'll pop up this window here. And then you go to Browse, and then you search for wherever you saved your par charge file. And then you have to choose manually, like how you want to visualize it. So you open this file, you drag or you scroll down this drop-down menu for a while, and you eventually get to the VASP menus, and then you choose par charge file, so that's what we're going to be visualizing. And then once you do that, load all those up, it'll give you a couple of different options of charge density to view. So the first one they give us charge density spin up plus down. So that would give you, well, kind of how it sounds. It plots both the spin up and the spin down densities on the same plot. So you get the full charge density. Whereas for option 3 and 4, you can specifically choose spin up or spin down. So you can visualize like, well, where your spin up orbitals are and where your spin down orbitals are. And they also give a fourth option to do spin up minus spin down, and that would be like if you were looking for magnetic materials, that would tell you which orbital is the magnetic one in the material. But usually we don't do that, so options 1, 3, or 4 are what we normally do. And then the all K files, they don't have position files associated with it, so you have to upload a postcard. So otherwise, so you can view your image more completely. So you just go to Browse again, get your postcard file from wherever you downloaded it to, and choose the VASP postcard file from your drop-down menu. Yes, Dave?
So your postcard file doesn't have to be like .xyz or nothing? Just postcard?
Nope, it'll read postcard. It'll read postcard, concard. It'll read XYZ too, probably.
So you wasted a year of converting everything into XYZ? Sorry.
Don't feel that I wasted a year converting all mine into cubes. So I realized that VMD would do all K files.
But do you need the postcard or concard? Which one is better?
Well, ideally concard. Like if you're viewing, if you have you want your right position file for the orbitals that you uploaded.
Then
So
we should have to use.
Well, if
and normally it would be a postcard from your
especially if you do molecular dynamics or your molecule moves through the cell and you use postcard instead of concard, you have atoms here and orbitals there, and you give a little surprise.
So yeah, that is a good point. You want to make sure that your position file matches up with the par charge, or else usually it doesn't look too bad. Some orbitals are just offset a little bit from your atom positions, but yeah, if you're doing molecular dynamics, things could look a little drastically different. So then, now that we're done uploading all our files, the fun part of VMD is continuously going through, choosing how to visualize them. So we go back into our main menu where we uploaded, we click Representations. Now open up a graphical representation files shown on the right. And this drop-down menu here, you can choose whether you're looking at your orbitals or your position files. So right now it's just looking at the par charge files. And then once in the bottom left corner, this is what initially usually shows up as. So you have your orbitals and then some sort of figure, which is represented by your postcard here. And then we can change this by changing things in this graphical representation tab on the right. So the first thing to do is to make it the atoms look nice. We choose our postcard file, graphical representations, in the top right corner. And then we go down to our drawing method and then click the drop-down menu and go CPK. That's usually, well, for semiconductor materials, that's the one I usually like to use to visualize the atoms. And then it turns all originally small dots into bigger dots. And then you can change those too in the drawing style. There's some options. You can change those as well to optimize it.
Which drawing style? Sorry, can I?
Yeah.
Which drawing style would you set up if you, instead of orbitals, if you make a movie of molecular dynamics, where bonds are continuously forming and breaking?
So then you'd want dynamic bonds, properly titled.
Yes.
Good. And in there, like you set a threshold for your bond length, so you tell it if you know your normal bond's like 1.4 angstroms, you'd set it to like 1.3, 1.4, and you can see bonds breaking and forming. But usually when you have systems of more than one type of atom, the dynamic bonds doesn't look so nice, so that's why I didn't put it in on this one. But then, so then now we choose our par charge files up in this top menu, and then we can play around with how to visualize the ISO surface of our par charge. So I'm going to go to the next slide real quick before doing that. So how to change your ISO surface. So that's one of the menus, or one of the things you can change down this tab here. And then there are two different cases that kind of illustrate the...
If you're seeing, if any of us are seeing it for the first time, I'm trying to repeat it. The first thing that comes up when you see this one, there will be no orbitals, only your model, and here it will tell the dots. So this drop-down menu should be changed to solid surface. Otherwise, it will try to draw isosurfaces, orbitals, by tiny dots, not seen for human eye, and human starts panicking, like, where are my orbitals? So this one first, and then things that Aaron is presenting.
Yeah, so I did mess with it a little bit, so I changed it to solid surface. And normally it also has it in a box too, and I don't like the box visually, so you change that in the show menu just to show the ISO surface and remove the box that it's in. So then, so you get those, and then the change, like, well, the density that you see from your par charge files, you change the ISO value. So the closer to 1 is, the smaller your orbitals will be, and then the closer to 0 is, like, your charge density just blows up. And then usually a good value that I usually find is 0.01 or 0.001, but that's usually probably system dependent, and you just gotta play with it to make your orbitals look nice. And then just going back, you can also change different ways to visualize them as well. So you can change based on coloring method. So you can change them all to a different color by choosing color ID. Then right next to that you can change colors. And then there's all sorts of different ways that you can visualize them. You just kind of have to get in and dig around with it to see what looks good. And then, yeah, that was the end of how to...
Oh, so let's talk cloud. Okay. Questions about plotting orbitals? 1, 2, 3. Crystal clear. Now, let's think once again. So Aaron did smart. He split his presentation on several chapters, so he will get more applause. Next chapter presented again by Aaron is oscillator strengths for spin orbit calculations, which will be general introduction into. So we are going. So proper bring it to. We need in most of our modeling to describe optical properties of molecules and materials, and the simplest thing to characterize optical properties is so-called absorption spectrum, which is related to the concept of oscillator strengths and transition dipole. These things that determine optical properties can be computed based on a set of orbitals in the independent orbital approximation, although if you are a skilled user of Gaussian, you'll immediately think best method to compute spectra is TDDFT. Right? Here we use a little lower level calculation. We use independent orbital approximation that is qualitatively reasonable, and it is the only method available if we deal with more than, let's say, 400 atoms. So it is not most precise, but it is much cheaper. Now, the approaches that we are using
can be cast in 3 different ways, and we have 3 different sets of codes. One, if system is in a singlet, if we do not discriminate between spins. Second, if we know that there are spin multiplicities, spin polarized case, if spin up and spin down electronic structure is a little bit different. And the third most advanced that we started very recently is when up and down spins are mixed, so-called spin orbit representation. To save time, Aaron is starting not from the simplest, but from the most complicated. But we should understand that it is a little bigger ladder, and we can return to older versions as we need, or sit down and discuss other things. Okay, introduction is done. Floor is yours again.
Yeah, as Dimitri said, we're kind of going backwards through this, but hopefully after John's presentation, some of what we talk about here will make a little more sense. So, oscillator strengths for spin orbit coupling. So, the difference between whether something like maybe spin polarized transition dipoles or oscillator strengths and regular oscillator strengths comes down to, I guess, the form of the wave function that we're dealing with. So, for spin orbit coupling calculations, the wave function is described by a 2-state spinner. That's just the solution form that it takes. And then when you're doing transition dipoles, you get extra cross terms that normally don't appear due to quantum mechanical effects. So going through our derivation here, when we take all these dot products, we're going to get 4 terms because we have two component vectors. So we get here what would initially be our transition dipole for just the alpha spins for this term here. And our last term would be the transition dipole for what would normally be our beta spins. But then due to spin orbit coupling, which mixes alpha and beta states, or your spin states, we get these transition dipoles for what would be classically considered spin forbidden transitions. So we get a cross term for a beta spin with an alpha spin and an alpha spin with a beta spin. So we get 2 extra terms for
The last term is phi beta or phi alpha.
Yes,
Okay.
it was not
Yeah, amazing.
scanned well enough.
Yeah, that's why. Yeah.
But, yeah, so that's the motivation behind the difference between spin orbit and spin polarized, and why there's a different methodology needed. So the rest of this will just be basic introduction on how to run oscillator strings for spin orbit, and then output files that they generate. So the only input files needed are the wave car from your generated from spin orbit coupling jobs, which is run from VASP non-collinear spin, because you can't run a spin orbit job just from running VASP, or running VASP how we normally run it. Like when you tell VASP run, you say run VASP. For spin orbit couplings, you have to run VASP _ NCL. So just a technical thing. Then we put in our input overlap file, so that just tells it which orbitals we're looking transition dipoles for. And then the energy pop, which is basically like our states file, but just for the orbitals that we want to look at. And then we call the script that computes the transition or the oscillator strengths for spin polarized jobs, which is in this directory here. And then it generates 3 output files. So oscillator strength CC, oscillator strength VV, oscillator strength VC.
Which stands for?
Oh, okay. So, as far as I could tell, I talked to you in a little bit too. So, for CC, those are oscillator strengths for just considering transitions within the conduction band. So, CC, conduction, conduction. VC would be transitions from the valence band to conduction band, which we would normally associate with our optical transition. So, this was the one that you'd use for to generate spectra. And then VV would be transitions within the valence band. And then I think we need the CC and VVs if we're computing excited state relaxations. So if you want to know the transition between different excited states, you'd have to know these oscillator strings. So that's why there's a difference between all these. Yep, that's the end of that.
Okay, let's thank Aaron. Any questions?
questions? If no, let's let Aaron to have a little vacation for, I don't know, 10 minutes. And now it's turn of John, who will go into more details how oscillator strength is computed.
Okay, so can you see the slides on the screen?
Do you have them in? We have 6 slides per page. Can you do it 1 slide per page or PowerPoint?
Yep, give me 2 seconds.
Sure. 1, 2. So the system that we are using is inherited from a military base in Grand Forks. They decided to be good neighbors and share it with university, but it is typically used for like conference calls, like giving orders or checking how the orders are completed.
Okay, let's see if is this better?
It is so much better.
So much better? Okay, perfect. Okay, well, like Aaron and Dr. Killen both said, we started with the more complex version of looking at what a transition dipole moment and oscillator strengths are. So what I'm going to do then is kind of quick go through the simplistic form of transition dipoles and oscillator strengths. And so on this very first page, you can see 3 equations down on the bottom. So the very left one, Dij, is related to a transition dipole moment. The middle one is the oscillator strength, which you can see is proportional to the square of the transition dipole. And then the last equation, alpha dependent on energy, is actually for absorption, but we won't talk about that right now. Okay, so just going back a little bit for what the transition dipole and where it comes from. So the simplistic form is just looking at the charge of one electron moving from one orbital to another. And so when you look at this phi I, r, phi j, dr, we're just looking at the electron density overlap between the 2 orbitals that are of interest. So if we're really interested in where we actually get these values, and for things that often get tucked into our supporting information, are the equations that are more or less presented on the screen, going back to looking at Kohn-Sham orbitals in terms of a momentum representation, and then transferring them to the transition dipole moment, which is the top right equation, and also having the matrix elements of these defined as this d, g, comma, g prime, and then putting them back into this equation for on the bottom right with this dipole operator being in terms of momentum. So we're interested in the transitions between 2 states and how these wave functions are overlapping between one another. So then the other more simplistic way of thinking about oscillator strength is the top rate equation, right? So it's just Fij, and as I said earlier, it's proportional to the transition dipole moment squared. But the experimental reasoning kind of behind what a transition dipole is comes from 3 terms of Einstein coefficients. And so the sigma value here at the top middle is considered the absorption cross-section for some type of absorption. But there's 3 types of this in terms of just your normal absorption, this B12, the term of stimulated emission, which is B12, which is more or less having some type of laser or frequency come through that's equal or very close to the transition energy, which moves the electron from a higher state to a lower one. And then also the spontaneous emission, which is this A21, which is what we would know as just a radiative type of recombination. So those are kind of really brief backgrounds on these 2 values. But like I said, the 3 equations on the very first page are more or less what we use when we're discussing things and explaining it to people who might be interested in what we're doing. So on this slide on spinners, Aaron briefly touched a little bit on what this is. So when we look at closed shell type systems with no spin polarization, wave functions are defined as one way. Our Kohn-Sham orbital bases are defined one way. When we look at spin polarized calculations, we can separate them into 2 distinct alpha and beta type orbitals. But then when we look at spinners, we're interested in the combination of both because they don't necessarily exist separately, but we're interested in how they interact with one another. So the 2 most important equations from this slide are going to be the ones in the top left, just looking at the form of what a Kohn-Sham orbital spinner orbital looks like. And then the one in the very bottom right should look very familiar because Aaron had it written up on his screen. So if you look at just the transition dipole up at the top right, it's just phi I, R, phi J. The same thing here, but now because we have roll and column vectors, the spinner orbitals get put in, and that's how we can do that. So if you're interested in a little bit more about the rest of it and how spinners get implemented into the DFT solutions, there's more equations here, and we can talk about that later. So more for the technical side of things, which is kind of the point of this, is we're interested in how can we calculate these types of transition dipole moments for different types of systems. So for the non-types of spin polarized, there should be a directory. If you're on HPC, I'm generally in the Killen lab account, and I would assume it's very similar in the Killen account. So you're looking in your bin, and then there should be subdirectories of OS and spin OS. And so inside of those directories, we'll have multiple versions of this OS underscore dipole underscore version something. So for just the standard closed shell, the OS dipole version 3 will be the one we'll want to get. And so after this slide, I'll go through and just show little bits of the code and some of the output. And so that's in the terms of what Aaron was talking about earlier, when you're looking at the output of his VC. So if you're just looking at the optics, this OS dipole version 3 is what you need. For any of these, if you need to go in and make modifications or you're curious about what's going inside the code, just look for the .f, the Fortran version. And so just make sure you don't delete it from the bin, just copy it and take a look inside whatever directory you're working in. A second one that's more used for the emission codes that I was interested in is this version 3B. So this not only calculates your optical transitions across the band gap, but it also takes into account what Aaron was describing as VV or CC. So all the intra and interband transitions are prompted into the OS strength output file, but they're also put into a matrix form listed as a 4-master equation file. And then finally, for the spin polarized, you can go into the spin OS directory and find up and down codes that'll work for both. So just a quick look inside of these Fortran files for execution. So 3 files are more or less generally needed: an input overlap, an energy pop, and a wavecar file. We talked a little bit about a wavecar file. We haven't really discussed what the structure of an input overlap file is. And you basically just create a new file called input overlap. There's 3 lines of it. The first line is the first orbital you're interested in. The second line is the last orbital you're interested in. And for running these dipole scripts, you don't need a third line. But because we all copy and paste the input file or input overlap file from directory to directory, the third line is usually just the number 1, and that gets run our coupling scripts.
So we have a little break. I think John will realize that he needs to redial. Well, John is redialing. We can enjoy working on ourselves.
Okay, so I was talking and asking questions, and I realized I was frozen.
John, can you please share the content once again? Because right now we see just our smiley faces instead of your slides.
Yep. Okay, so where was I when this cut out?
Your first slide with technical details on Fortran code.
Okay, here?
Yes.
Okay, so I don't know if there's any way for me to show my cursor on here. Otherwise, let me just, oh, never mind, I need to install something. Okay, so what I have highlighted in yellow in this Fortran section of the code, I just highlighted the words open. So if you're curious about what files you might need for this type of script, you can look for these open keywords, and it'll try to prompt something in. So this first line, right, it says open input overlap. The next open is trying to read this energy pop file. And then further down, you see it say open OS strength. That's not to read it, it's just to open it to write into. So you don't have to worry about that. And then open on the bottom. Did I describe what an input overlap file sounds like?
Yes, yes, you did.
Okay, all right. So the energy pop file is basically, you take the converged energies from the last electronic iteration step in the outcar, and you segment only the states that you're interested in. And so you can see the very middle line, more or less, underneath this open energy pop, it says read 11. And so it's looking at the number of the state, this NNI, the energy of the state, E, and then looking at the occupation of the state. So it's just going to go through and read all of those and take that information in, and using the wavecar generate the oscillator strength files that we're interested in. So here's what a small section of the code looks at. So you have this OS strength, which is the main oscillator strength output file. So you can see that within the Fortran code, you have this OS strength file is creating, and then it's also formatting it on the second to last line of the first picture. So you're looking at, you know, your initial band, your final band. You're looking at the oscillator strength value for that specific transition, the change in energy between those two specific orbitals, and then also the population of orbital 1, your initial, and the final orbital. So those are the main ones that we're generally interested in terms of converting this oscillator strength file into our absorption spectra at the end. And so on the bottom is just a picture of what an oscillator strength file might look like in terms of the values. For code, sometimes the headings actually pop up. For some versions of the code, there is no heading, but if you're interested in, or curious about what they might be, you can just look into the script itself for the format. And then for spin polarized calculations, when you have the converged ground state for an I spin equals 2 system, again, what we're going to need is an input overlap, an energy pop, and a wave car. And so in the spin OS directory, there should be a spin up dipole script. And it's going to require the same thing that was needed for the non-spin polarized version of the code. And so it can be run in the same way. The main difference comes up from looking at the spin down system. When you look inside the code, you can see it's prompting for a differentiation in the energy pop of the system itself. And so it'll look for an energy pop down. So when you look at the 2 spin components in the end of the out car, you take your orbital range of interest from spin component 1 for the spin up, and then the orbital range of interest for spin down from the spin component 2. And then you can use those to generate the OS strength files that will say OS strength down. And then from there, you can more or less just go forward the same way we would with non-polarized calculations and just run them individually up and down to create absorption spectra. And I think that is a quick look at running these.
You're not going to show any spectra?
Oh, I can pull some up.
Because if some of us are seeing this machinery first time, it is very boring to without illustrations.
Okay.
Okay, let's make agreement. You just send email with examples of spectra to all who was in the list for meeting announcement.
I can do that.
And Dane requests your slideshow. He wants to learn your codes.
Okay, I can definitely do that.
Okay, let's thank John. Any questions? Aaron has one.
What are common errors that occur when you try to run the OS dipole v3 script or any of the oscillator string scripts?
So some of the things that you need to take into account are the orbital range. I mean, if you have too big of an orbital range, the script itself is going to run out of memory limit for however big you allocated array size. So you can start smaller, looking at say a range of plus or minus 20 states from the HOMO and LUMO. Generally, I keep it under 300 total states that I'm interested in. For the closed shell systems, those are really the only issues I've run into with that. There have been a couple times where there's a few different versions of some of the 3B, more or less prompting inside of the matrix that's produced, like it says NAN, so it's just a general, not a number value put into a matrix element, where you can go in and just change those to zeros, because sometimes when you transfer those files into, like, say, MATLAB, it doesn't like this NAN value. Other than that, outside of using multiple K points, that was really one of the main issues in terms of trying to get these scripts to run. And I think I've mentioned before, trying to match plane wave number size can cause an issue too if you're moving from one set to another if the plane wave number size doesn't match the number of plane waves in the like the gamma point calculation or the calculation that's being run. So did you have like a specific error in question?
So you mean like when it reads in the plane waves from the wave car, like what would it differ from?
Well, so one of the issues that I found was, so at the gamma point, you have some calculated number of plane waves in the system. And then if you move to some other K point and you're trying to run absorption codes, it has an issue reading in the new number, because I think when it's looping through the actual calculation of the oscillator strings, it doesn't like when those numbers don't match. And so you get like a segmentation fault because some variable is trying to go past what it should be.
Okay.
More questions to John? If no, let's thank him once again. So we have 2 more talks for another 25 minutes, and the next one is hopefully brief. Section number 3 from Aaron. On I hope it is not a surprise for you.
Just didn't realize it was my turn. So I guess here I'll be talking about how to run heating jobs and MD jobs, and then a couple of things you want to keep track of while you're running these jobs. So initially, just some background for heating, like if you're going to do MD, you have to know the positions of your ions and initial velocities. So that's basically what the heating job does. It just provides velocities to all your ions constrained to the Maxwell-Boltzmann distribution.
Can you tell us a brief introduction why anyone heat molecular dynamics? Make connection to non-radiative transitions. Non-radiative dynamics. Why? There is only maybe 1 or 2 persons in the audience who is interested in molecular dynamics on itself. Dane and partially Dr. Han, but most of us are interested in dynamics of electrons. Why do we need dynamics of nuclei?
Because they live in the home of ions, and the ions like to move. So the ions their movement basically allows the electrons to dissipate energy if they're not in equilibrium or excited state. So that's why, that's why we use MD in the Cohen group. So we can give the ions some motion and then model the electron's relaxation very generally. So back to the slide. So we just need heating so we can do the MD. And then so for a heating in-car, this is just a general template which can be found in the bin, which you copy into your directory. So the basic things that we have to keep track of is the desired temperature that you want to heat up to for your MD run, which is very high for the last person to use this. And then number of ionic steps for how long it takes for your system to heat up to your desired temperature.
So if you hate someone, you need to give to him or her this template, because MSW equals 10,000. It will run for like 2 years.
Right, so I think that's just put there to catch your eye. Like, oh, that's wrong. You gotta change that. So yeah, normally like a reasonable amount would be like maybe 300 to get it up for first go.
For first go, 50 would be sufficient.
50? Okay. So then you want to keep track of the temperature of your system as it goes through its heating, because it's not going to heat in like 5 steps. It kind of takes some ionic time for it to do that. So you can find that by looking in the OSSICAR output from VASP, and then you can just grep T equals from OSSICAR, and it'll give you this line here. You can see for each step 1, it's at 300. Drift sound real bit, and then you can just track that for the entire trajectory that it's on. And ideally, you want it to stabilize at the temperature that you set at the in-car. So that's when you know it's ready to move on to your molecular dynamics. And then just to know that you've done it correctly, you can look into your cont car from your heating directory, and you should see that your positions should still have a bunch of occupied numbers in there, but now your velocities should have a bunch of values too, because normally just for geometry optimization it's all zeros initially, because you have zero velocities of your ions, but now your cont car file has positions and velocities, so it's ready to go into dynamics. So then you just copy the cont car from the heating directory into the directory you're going to do your molecular dynamics, which you can do with this command shown here. And then you copy in the molecular dynamics in car into the directory you're running, and then this is just the general template that's found in the bin as well. And again, you will just want to set the temperature begin and end for the temperature that you want your simulation to run at, and then the number of ionic steps for your trajectory. So in the clean group, a picosecond is a nice number for a lot of relaxation mechanisms that we do. So we set it to 1,000 because the way that it's set up here, the pot IM is at 1, so that indicates 1 femtosecond per ionic step. So then we do 1,000 steps, that gives us 1 picosecond. So if this pot IM was a half, you'd have to do 2,000. So that's kind of, there's an interplay between those that kind of have to keep an eye on as you're doing your MD. So you set that up, and then you run your job for a week or a month, however long it takes, and then you can visualize how the energy of your orbitals change during the trajectory. Because you can imagine, as the ions move, and then you can kind of isolate, if an electron's coupled to a certain vibration, you can kind of, you should be able to see that from our energy fluctuations chart, which I've shown here how to plot. So there's a Perl script in the bin that extracts energy from the outcar file, I believe. And then you put in 2 numbers at the end of the script, so a number of orbitals below HOMO, above LUMO. So if your HOMO is 80, you put 60 and 100, so you can get a wide range of orbitals to look at. And then that Perl script gives you an output energy by band. You just copy that to B, because that's what the new plot file looks for when you plot it. And then that new plot outputs this is the figure here. And then you kind of see some coupled oscillations are really prevalent around the 400 to 800 time steps.
You are the only participant in the conference.
Usually it's good to look at this chart because you can tell if there's something's abnormal about your system, or you can look for interesting characteristics of it as well. So it's just a good characterization tool for any molecular dynamics job that you run.
So what is the feature you mean abnormality?
So like if maybe an atom broke off, like a fragment broke off during the MG trajectory, you should be able to see changes in the energy fluctuations because your electronic structure is going to change dramatically. Because I know like John, his last perovskite project, he had formations of iodines during the trajectory. There was a C, like there's a line that went way up into the middle. So that gives you an idea of whether there's some sort of chemical dynamics occurring during the trajectory.
So the project, Aaron is so humble that he gives example of project of others, but he's running a project on quantum dot that we discussed 3 weeks ago here. And if a quantum dot doesn't have ligands on the surface, there appear states that come inside the gap, close the gap, make it dark, right? If during molecular dynamic one of the ligand from the surface detaches, the surface state is recreating back, and one would immediately see it on such diagram.
Mm-hmm.
Right?
I wouldn't pretend that I knew that beforehand. as a practical application.
I have a quick question. So, what do all these different colored lines represent? So, how come there's so many of them?
So that would correspond to the input number. So like here, HOMO minus 20, LUMO plus 19. So LUMO would plot 19 orbitals.
So please show us where is LUMO.
So LUMO would be
And which color it is?
this orange one. Is that orange? Yeah, this orange one here would be a LUMO. And then the black one would be your HOMO.
Okay.
And everything below it would be HOMO -1 and so on.
Okay. I got you. Cool.
Daniel, you had questions?
If we're good on that, I think that was the last slide I had.
Okay, let's thank Aaron. More questions to Aaron?
Is there a way to plot that with just the HOMO and just the LUMO rather than have all of those other lines? There's-
Yep, you would just put in one and one. Yeah.
Is there any benefit to having all those extra ones?
Yes, if we need transitions between them.
Do you have a question, John?
John?
Yeah, so I just had a quick question, right? So even looking at like his fluctuation plots, I mean, you can see that there's orbital indices switching, like even around like 500 femtoseconds. You can see the orange one looks like it should actually continue up into the gray.
Right.
And so I'm just curious, is there any way we could write something to find a more natural fit so that we actually could negate orbital switching? So like if you look at like 450 femtoseconds, you see there's like a intersection between the orange and gray, the LUMO and LUMO +1, and then
This
you
line
see,
should continue up, and this gray one keeps going down.
right, that would be like a more natural fit to a line. I'm just curious if there's a way that if we could write something to naturally plot instead of having such sharp transitions to account for this type of indice switching, or if it would even be helpful.
There's no way to track that number of band, right? In our system.
John, you're asking a provocative question.
Yeah, it's a little above my pay grade.
Right now, we identifying orbitals based on their number, which is natural and simple. But if one would identify orbitals based on bond order or shape of orbital or decomposition over atomic orbitals, then your idea would be realizable. But it is a lot of extra efforts that we just lazy to commit.
Okay. I just didn't know if there'd be a way to, just look at simple values and try to extrapolate where, the next step should be instead of just on these simple numerical energy values. That was all. But
No.
Thank you.
Okay, so in the last 10 minutes, it will be most important and most intense talk by Dr. Han. So what are we doing? What is the goal of all this activity? If you put aside maybe 10% of effort in the group about molecular dynamics itself, the rest of the main effort is to predict the change of occupation between electronic states. So to do electron dynamics. And it is done in the group by MATLAB codes. But these MATLAB codes need parameters for transitions between orbitals. And these transitions between electronic states induced by nuclear motion is 1,000 times more heavy than everything we talked before. It's most numerically complicated procedure. Dr. Han, you will give us introduction into the way how to compute this rates of transitions between electronic states because of nuclear motion. So this is one of the most important, it is the most important things we do.
Yeah, so just like Dr. Kinney said, so this is one step before we run the MATLAB code for electron dynamics. So Aaron has already talked about this part. So this is just an example for the tracking of temperature during the molecular dynamics. And so after we have finished the molecular dynamics simulation, we create a new folder and we transfer all of them to this new folder, and we run this per script. So basically, this is from the outcome, we can convert the atomic configuration to this position file. Since we run molecular dynamics on 1,000 time step, that means we have 1,000 position file. So by running this code, we can have P000 to P999. And we also need 2 additional files. This is energy pub and the input overlap. So we can get these 2 files after we done with the geometry optimization. And we also need in-car coupling. So this is also in the bin in the HPC. So finally, we need this kind of specialized script, and we need to make 2 modifications at line 31 and line 43. We need to change the orbital number. So just make sure this number should be consistent with the input overlap. And after that, we just run the script by using the qsub command. So if everything goes well, you can see we have this new file like coupling 000. So this is a non-adiabatic coupling for non-spin. So for spin polarized, so the procedure is pretty similar, but we need another in-car. So this time we use the in-car for coupling spin. And we also need a new B script. This is a B script.
Your call will be disconnected.
Okay.
John, you will see the recordings if you get disconnected.
Okay. Let's go. Where is my script?
Come on, it should be disconnected 10 minutes after, not 10 minutes before. Okay.
Okay, so if the job is running successful, then we will have 2 subdirectories. We have up and down, and each of them contains some files like oscillator strands, like coupling files. Okay, so finally, we can do non-adiabatic coupling for spin orbital coupling. So ideally, everything should be consistent. Like we do geometry optimization considering spin orbital coupling, and then we do molecular dynamics considering spin orbital coupling. But actually, if we do that, the computational job will run for infinite time, so it is not possible. So as an approximation, we can use spin polarized molecular dynamics. So this time we can save lots of time. And for the non-adiabatic coupling simulations, we need input overlap, and also we need 1,000 files for the front molecular dynamics. And we also need a specialized in-car. And here is the standard template. And then we need additional program, spinner exe, and B script. So we use the qsub command to initiate the coupling calculations. So that's it. Here I show the content of the B script. And that's it.
Okay, many thanks. Questions? I do have a very important question. If you do the procedures that Dr. Khan is showing, are we wasting time? Is it just to torture our patients, or there is a important outcome? Like through looking on this, what is the outcome? What do we expect to get? So before asking the speaker, please try to think about it. Like when we discussed jobs for optical spectra, we were getting list of oscillator strength values for different transitions that can be converted into spectra, right? Images, spectra that can be converted to experiment. What are our outcome data if we are making jobs for these non-adiabatic transitions? Just close eyes, think for 5 seconds.
try that each of you may try to answer it, and then let's give chance to Yugun to answer it. Huh?
Charge transfer.
Charge transfer is a very, in some sort it is correct, but you give a great strategic bird's view picture. Yes, if you can compute non-adiabatic dynamics, it can be converted into analysis of charge transfer dynamics. But right now we are thinking not as strategically. We need just the very important technical data without which we cannot go further. Technical data that allows transitions between orbitals.
So does it just give you output files that you use in future jobs, other jobs, so that?
Correct. Yes. Yes. And now we need to understand which type of output files is being generated.
I guess for me, so the most important output is the evolution of electronic configurations like the orbital energy versus time. So by using this information, we can compute like photoluminescence.
Absolutely correct. If we answer this question at the end of group meeting when we will be describing MATLAB procedure. But if you stop right here, what is the outcome of this bscript.sh? If you submit it, what comes out?
So at each time step, we can get the oscillator stress
And
and the coupling file.
yes. So what are coupling files? What are their structure? What is how many coupling files and what is encoded inside?
It's just a matrix, right?
Yes. So matrix where rows and columns encode what?
Transition level.
Not transition type, but intensity of the actually non-adiabatic coupling. Intensity of probability of transition from orbital I to orbital J. So for rows and columns and enumerate orbitals, like if you have 100 orbitals, then you have 10,000 pairs of orbitals. And you will have transitions from each to each. Those will be saved in coupling files. How many coupling files? Is it one or more?
So we have 1,000 position file. That means we will have 1,000 coupling files.
Okay, why? Why we should pay so high price?
Because it's going down electrons in the lower band. So finally, from hot electron is going to the low mode
I guess that's the same argument about the
with the time.
ensemble average versus
Exactly.
long trajectory.
Yes, yes. So if we compute, so in order to compute these couplings, and we will make another meeting going through the derivations, but we compare wave functions at time t and times t plus delta t. We see how electronic structure changes on the small time increment. But if you make this comparison today, tomorrow, next day, since nuclear trajectory is different, the response of electronic system will be different. And couplings will change their phase. They can be of the same absolute value but different sign. Or they can do a little change, which will be not representative. So in order to be realistic, one needs to run for a long trajectory and make average. Add together everything along the trajectory and then divide by number of steps. And then the average coupling will be reasonable to describe the dynamics in real world. So 1,000 positions, 1,000 nuclear configurations along trajectory, and then 1,000 coupling files. So this long calculation, it will be 1,000 times longer than single point. And then it will generate 1,000 output files that we need to process. their names will be coupling.000, coupling.001. And depending on whether we are in singlet, spinless, spin polarized, or spin orbit, they will have their specific features. More questions? Let's thank Dr. Khan and presenters. So I know that right now it was a little heavy because we were doing our regular activities and suddenly we jumped into this heavy numerical protocols, but it will pay back through the research. So next time let's do posters, which means you will